Yeah, yeah. So we're academic brothers through the academic tree through Ichiro. Um, yeah. So okay. Um, yeah. As Jay said, I'm going to cover sort of high level a bunch of the different autonomous systems that we have, but I'll drill into one of them. Um, and I'm guessing that most of my slides won't be necessary, but because right, you guys already know about autonomous systems, but I'll pick and choose some content that I think is important to mention. Um, right, so right, NIST is part of Department of Commerce, and we have some Nobel Prize winners in the last, I think, 30 years, five Nobel Prize winners. Um, and we have, if you're interested in, after hearing this talk, if you're interested in potentially doing a postdoc with us after, studying at University of Toronto, then please contact me, and we can look at trying to apply for some funding. Right. So arguing for the motivation of autonomous, I'm guessing is unnecessary at this point. We at NIST have a lot of collaborators in industry, applying these autonomous systems. Um, and as Jay said, so we've been doing this since 2015, 2014. We had a success story. In 2015, we had autonomous control over an X-ray diffraction system at Slack, uh, and we were thinking to publish it, but then decided not to because we thought maybe we can use this autonomous system to make a major materials discovery. At the time, there were, I think, three major players in autonomous, maybe, I guess four. So there's Alan at, where you guys are at, who's focused more on liquid systems. Benji, who is doing carbon nanotube process optimization. And we were trying to do materials discovery for solid state materials. Um, and we held off on publishing until we actually made a material discovery, which I'll talk a little bit about. Um, and right, so we have three different modes of autonomous that we're focused on. Is the simplest one, which is non-autonomous, is just having AI provide guidance, building a recommendation engine for the user. The other one is putting AI, putting machine learning in control of the measurement tools so that they're optimizing your measurements. And the last one is controlling the entire lab. So it's making materials, it's measuring them, and making decisions on which materials to measure next, to explore next. Um, and one argument I like to make for the difference between a typical autonomous system that we hear about for vehicles and the autonomous systems that we need in the physical sciences is that for an autonomous vehicle, you want it to take you from point A to point B safely. You don't want it to explore, to try to discover something new, right? You don't want it to drive past a grocery store and think, oh, I've never driven through a grocery store before. Let's see what happens, right? But that's exactly what you want our autonomous systems, the autonomous systems in the physical labs, to do. You want them to look for something anomalous, something interesting, and to pursue those studies. And this is a slide I just added last night. Uh, and I was thinking this is something useful to think about, something that I do when I listen to talks about autonomous or read papers about autonomous. Um, these are sort of critical thoughts that you should bring in when you're listening to these things. So the first thing was a lot of people say they're doing autonomous studies, but often it's just done in simulation. And you only find out that it's just done in simulation by asking, was this only done in simulation? Was this put in actual physical control of a system? Because what you'll find is that there are sort of fundamental challenges that you have to address in machine learning and in the physical sciences by applying your AI to control a system. The most relevant is typically that data is not clean. Data does not come in as it does in a simulation, in a DFT simulation or X-ray diffraction simulation, right? It has noise, it has data artifacts. You get weird stuff happening in your data. And being able to properly handle that is fundamental to building a real autonomous system, in the real world. Um, Also, this is a challenge. The second one is something that was more a problem in the beginning of the field. Is it really autonomous? So often people would say that what they're doing is autonomous, but if you drilled in the supplemental, you would see that there's somebody in the background modifying something regularly. And so then you see this general progression of performance. But if you read it in the supplemental, that performance increase is primarily due to someone sitting in the back modifying something, right? So you have to look for that. Um, there's another question of should this be autonomous? uh, a lot of applications of autonomous tend to be, or a lot of publications in the space are about making things that are autonomous, making things autonomous that have no need to be autonomous. If you have a scanning system that's able to scan an entire wafer, right, an entire a sample, and you're using machine learning to guide which point on the sample to measure, um, but those measurements take milliseconds or seconds, then there's no reason to not just scan the entire thing instead of have machine learning in the loop, right? What machine learning costs computational time. Why waste that computational time when you just take the entire measurement, right? So that's another question to ask is how long does it take to run to collect one piece of data? Can you collect all that data in a reasonable amount of time? Do you really need complex machine learning to run your experiment, right? So that's a question you right. Um, People won't mention these things, how long it takes to do their experiments, and because this is sort of a hot field now. So um, being able to know to ask that question, was this a legitimate application of autonomous tools? And the last one, or the second to last, I guess, are their discoveries useful? A lot of groups will say that they've used active learning, Bayesian optimization to discover, 100 new materials, 10 new materials, 5 new materials, and they'll even patent those materials. But then the question is, are those materials actually useful? Because the space of potential materials is insane, right? There's so many possible materials we could discover, but typically those aren't better than the materials we already have. So when they say we discovered these, 10 new materials, to say um, how do they place in the current state of that application space? And then the last thing I want to say is that there are different challenges between chemistry, liquid handling chemistry, and solid state physics that typically in chemistry you can manage to say I'm going to mix these liquids and see what happens, what the property of the material is going to be, and so then your input is just mixtures of source materials. In solid state physics, autonomous has another challenge that you have this sort of fundamental rule that you need to learn, which is the combination of how did you make the material, which includes how did you synthesize and how did you process the material, and then um, uh, um, that results in the structure of the material, the lattice structure and the microstructure. How did the atoms form? How did the grains form? Right? Or what's the form of the grain boundaries? Right? Those have a fundamental impact on the property of the material. Right? How the lattice, how the atoms are organized impacts the property of the material. How the grains are oriented impact the material. So in solid state physics, we tend to have a significantly different challenge. I would say more difficult challenge also because also our most of our synthesis and characterization has to be done, a lot of synthesis has to be done in vacuum under extreme controlled conditions. So as opposed to just managing liquids. So any questions on this before I dive into, you know, some of the fun stuff we're doing? Okay. Okay, I just think this is, I realized that this is something that I do whenever I read a new paper or hear a new talk. I go through these things and I ask myself these questions, and they help you figure out the utility of what you're hearing, um, the value. Yeah, yeah, Jay.
Yeah, I mean, Gilad, you're really preaching to the choir. This is a group of kids that have had to listen to a semester and a half so far of me asking, was machine learning even necessary? Did we need to do this, or should we have done linear regression? So
Right.
everyone from my class is just, yeah, yep,
Okay,
yep.
great, great. Yeah, yeah. Okay, awesome, awesome. Um, Uh, yeah, okay. And so then at NIST, we have a bunch of different efforts, mostly based around building open source software and platforms and using those at user facilities. And then we also work on teaching and building trust, and I'll dive into that. So I'm part of a group at NIST, and one of our main focuses in autonomous systems is this field of physics-informed machine learning. So it turns out that when you're applying machine learning to physical sciences, you will get answers that are mathematically correct based on the math of the machine learning, but they are not necessarily useful to the scientist because they could be completely unphysical, right? The analysis of the data could be wrong. The analysis of the data could be correct based on the machine learning algorithm, but completely useless in terms of physics. The predictions it makes could be could be non-physical. The decisions it makes could be non-physical, or not beneficial for you. So by encoding prior physical knowledge into the algorithm, you can get dramatic boosts in performance. And that's something that we've done throughout our algorithms, throughout our autonomous systems. And this includes prior physical knowledge of the synthesis system you use to make the material, the processing system, the um, the characterization tools, right? There are rules of physics that are associated with X-ray diffraction, neutron scattering, scanning probe microscopy, and by encoding those physics into the model, you get dramatic boosts in performance. And so that's something that we do. And here are the 9 types of autonomous systems that we have at NIST, right? So we've been doing this for a while, right? Since for over a decade, we've been building autonomous systems. Uh, Jay has been part of a bunch of these too. So um, uh, I'm going to go high level, talk about these, and then dive into some more specifics. So the first one is the one that I'm going to dive into the most, which is autonomous phase mapping. Can we figure out how the relationship between how we make a material and the resulting phases, lattice phases, and microstructures of a material? And so for this, we have autonomous control over X-ray diffraction systems, both at the beam lines and in the lab. Then we've also done autonomous neutron scattering. So then you load a magnetic sample into a neutron scattering beam, and you want to characterize the. Oh, I have this. Um, yes, yes. So right, like we can control some aspects of the neutron scattering system uh, to accelerate characterizing magnetic materials. We have a few projects in alloy design. So these are associated with optimizing uh, additive systems with in situ with X-ray diffraction measurements. Um, this is a new one. So we have a system for building carbon capture materials or direct air capture materials. Optimizing them for improving capture of stuff out of the air. And then, as Jay said, the corrosion-resistant film, this scanning droplet cell was Jay's baby, and we wrote a proposal on it at NIST to raise some funding. Uh, at the time, we were trying to convince management that this is the future, that autonomous science is the future. And they're like, no, everybody already does autonomous science. This is a decade ago. And we're like, no, like the machine learning is new, right? And they're like, no, no, it's already done. We had this battle, but we're able to convince management to get us some funding to start working on that. Um, one of the cooler things that we have is autonomous epitaxial growth. So in this case, um, these are pulse laser deposition systems. So, and I'll talk a bit about this, but the basic idea is that we can now optimize a material's growth atomic layer by atomic layer. We have a 3D printer that has X-ray imaging built in. So as you're printing the parts, you can optimize the printing to reduce defects in printing. Uh, we also have a bunch of systems in liquid formulations, and this is funded by 3M, Dow Chemical, Solvay, a consortium of large companies, Procter and Gamble. Um, and the main thing here is mixing liquids and mixing molecular sources and seeing how those molecules form together into new structures. And so then you can optimize soaps and adhesives and various other things. And then we also have a toy system, which I have sitting behind me, which we use for education. And this one costs, so these cost, I think, $30,000 each. And this costs $300 for each of these systems. Okay. Um, yes. So are these different things connected? They are. So they're connected in two aspects. One is we have one unified software package that we're developing across these called Hermes, which I can provide a link to. It's up on GitHub. Uh, um, but now we're starting to work on bringing them together in active control. So we have some papers coming out soon regarding that. Yeah, so that's sort of, newer stuff. But you could see how a bunch of these systems could work together to help accelerate knowledge of some specific material system. Okay, so we also run a boot camp, but you guys already went through a course, so there's no reason to advertise the boot camp. Um, although this is gonna be our 10th year running this boot camp. So in case you want to go to a party based around machine learning for material science, right? If that's something you're interested in, that's gonna happen this summer. Um, yes, yeah, we need more swag. And then we also run this competition, which might be of interest to all of you since since you guys are already educated in this. So every year we run a competition with a different company or group of companies where we identify a industry relevant challenge. We present that industry relevant challenge in sort of increasing complexity on Colab. You don't have to install anything on your computer. All the data is up online, and we have prizes. So this is the prize money is provided by Cell Matter and Cell Patterns, and so then you can win. I think like up to $1,000, something like that, if you win, in this competition. The most recent one was, you can see here, was can you accelerate phase mapping of liquid formulations? And this was a fun project related to the system that I talked about, and you'll see another slide about it. Right. So if you're interested in the competition, also let me know. Okay, the first example I want to give is the one that's the closest to my heart, and the one that we've been working on since 2014, 2015. And that's the idea of accelerating phase mapping. So are all the people here material scientists?
No, we're a heterogeneous mix.
Okay. All right. So then high level explanation of phase mapping is that, let's say you're trying to make some new materials, and you're making those new materials by mixing some cobalt, some nickel, and iron, but you're mixing it in different ratios. So sometimes you're making a sample that has more cobalt, right? So that can be visualized in this ternary diagram as a point over here. So it has more cobalt than iron or nickel, right? Or maybe you're making a material with more nickel, so that would be a point over here. If you have an equal mixture of these three elements, it would be a point over here in the middle of this ternary diagram. So when you mix these materials together, the atoms form together in different lattice structures, shown here, right? And those lattice structures are predictive of the properties of the material. How the atoms form, the ordering of the atoms predicts the properties of the material, not just how much cobalt and iron you put in the material, but also how the atoms self-order. And this is due to some sort of fundamental physical principles. And this diagram, what it tells you is how the atoms form. So it tells you that if you're making material in this space, mostly nickel and cobalt, these are the two lattice structures you'll see in the material, this one and this one. If you add more iron, you're going to cross a barrier, this boundary, and you're going to see a new structure introduced, a new phase, a new lattice structure introduced. And if you add more iron, you're going to see you're going to cross another boundary. And it turns out that these boundaries are fundamental in materials optimization. So it turns out that the better materials will tend to exist in certain regions of these spaces. So for instance, maybe the best material is over here, right? Or they'll happen right next to a boundary. So if you know what the phase boundary is, and I'll show you this, or if you know the phase diagram where these boundaries are and what the phases are, you can actually exploit that to dramatically accelerate materials discovery. And I'll show you that. And so this is part of this synthesis process and structure relationship, right? And then we can exploit that to optimize properties. Actually, I'll show you that right now. So this is the code that was used for our paper from 2020, which resulted in the discovery of a best-in-class material. So here we have a material system where we're mixing iron, gallium, and palladium. And the goal here for this example, this demo, this isn't the one that we made a materials discovery for. This is sort of the demo data set. So we can make materials in this space that vary in how much iron, gallium, palladium is in the material. And this is what the phase diagram looks like, right? Here are the boundaries. And what you can see is that, and what we're trying to do is maximize magnetic saturation. Which materials have the highest saturation magnetization? And I've color coded that here so the best ones are yellow. And what you can see is that they're all in this region here, or the majority of them are over here. So if we happen to know the phase diagram, we could just hone in on this region over here and ignore everything else, right? At least initially. And that would dramatically reduce our search for a better material. And so that's what this algorithm Cameo does, is it first, here in this image, in this video, so every time you see a sample circled in magenta, it means that we've made that material. That's a material that we're investigating, right? We're investigating, so the higher level thought is that we've made this material, we've characterized it, we've learned from it, and we're using that to then inform the rest of the analysis. And so initially what it's doing is it's trying to figure out what's the phase diagram. And at some point, you see here, it's gotten with I don't know, 10 samples or so, it's figured out what the phase diagram is, and then it starts aggressively honing in on where the best material is, right? Because now it knows that the best material is most likely to be here. So it doesn't have to search over here because these samples, these materials suck. And what we show is that by employing this physics-informed AI, this knowledge of phase, we actually build in the physics of phase maps into the AI. And the physics also, in this case, it also knows X-ray diffraction. So it can run X-ray diffraction simulations through control of Topaz through this software. It can hone in on, first it tries to figure out the phase diagram and then exploits knowledge of the phase diagram to figure out where the best materials are. And again, the reason for this is that when you're searching over a large space, it's possible that your optimizer will get stuck in some local optima. But if you can figure out where the phase boundaries are, you can say, okay, the behavior here is likely to be different than here. There's some kind of change that happens. So maybe let's consider searching on either side of this boundary or near this boundary, right? And this algorithm also has some other nice features that it's probabilistic, so you can you can exploit either other data. So if you have simulations of this data, of the materials also, you can use that as a probabilistic prior. So that's something we did. If you have exogenous data related to this material, you can employ that as a probabilistic prior. And we show that that boosts the performance. And with each new piece of physics that you employ, in this case, with this paper, what we did was we increased the amount of physics in the algorithm little by little, and we saw how quickly does it figure out the phase diagram. And what we found was that the more physics you employ, the better the performance. And specifically, employing physics in decision making seemed to have a dramatic impact. Okay, so I see that I have a question. Let's see what this is. Um, uh, yes, okay. Yes, exactly. Okay, yeah, excellent point. Excellent point. So there are two ways to incorporate prior physical knowledge into an algorithm, to a machine learning algorithm. Uh, there's constraint programming and there's a probabilistic programming. We tend to lean towards the right, towards the probabilistic programming. So in probabilistic programming, what you're doing is you're assigning a bias towards, you're assigning a prior leaning towards these prior physical expectations. But as you collect more data, that bias, bias becomes weaker, right? The data starts to, the impact of the data starts to swamp out that prior assumption. And at some point, you can actually cause the algorithm to just switch away from that prior. The alternative is constraint programming. And in constraint programming, you can impose hard constraints. And you only want to do that when you're absolutely sure. So for instance, a hard constraint would be, I'm looking at X-ray diffraction data. I want I want any analysis of X-ray diffraction to assume that I will not see a negative intensity because it's impossible to see a negative number of photons hitting the detector, right? So then that's a hard, you would impose that as a hard constraint. But you can also impose them as soft constraints so that you can again bias. It turns out that soft constraints are directly related to probabilistic programming. So it's sort of like applying probabilistic prior. So, but this is an excellent question, right? So in our algorithms, this is exactly what we do. So we put these prior assumptions in, but we make them so that the data can replace that. And not only that, the human can replace that. And I'll show you that in a minute. Yeah, but that's an excellent question. Um, and this algorithm, the nice thing about this algorithm is that we were able to use it to discover a new solid state material. And as far as I know, this is the only discovery of a best-in-class solid-state material. So for instance, Milad has discovered a best-in-class additive for a known material that boosts its performance. But in this case, it's a new material, specifically in phase change memory materials. And I forgot to add this. There's a new paper on this material. We've since worked with TSMC to build a device which has now been shown to be the best in class phase change memory device that TSMC is using. So, right. And in this case, the AI, yeah, it's pretty cool, right? And uh, uh, in this case, the AI that we use for Cameo, again, has built-in X-ray diffraction, knowledge of X-ray diffraction, and some fundamental concepts of phase map. And exactly going to this question before, in the phase mapping, there are different rules for equilibrium phase maps and non-equilibrium, right? So this is a place where exactly what you're saying, that you might want to have softer constraints based on the material system you're looking at. Okay, so since that work, we've done some other cool stuff. So one of the, for the same application of just trying to phase map, one of the questions is when you're doing science, typically you have an experimentalist who's doing one track of work, and you have a theoretician who's doing another track of work, and they're both complementing. Oh, okay. All right. Okay. So I'll be quicker. So I'm just going to zoom through these then. All right. So in this case, we were able to combine to make an algorithm that does both theory and experiments in closed loop. So, right. So you have machine learning that's running simulations. It's using knowledge from simulations to update itself and then decide which experiments to do. that those experiment data is used to update the model and improve the simulations. So you have this constant back and forth between simulations and experiments, and they're both being constantly updated. And there's a paper on arXiv. I guess I forgot to include that here. So if you're interested, I can share that. We also have human in the loop. So if the human is watching the autonomous system and saying, actually, I have prior knowledge of other similar systems, I think this is wrong. I think either your analysis of past data, your prediction for the results of future experiments, or your decisions on which experiments to do next are wrong. I want to impose my bias. The user can then just draw on the image of that the AI is providing, and that then is used in a probabilistic framework to provide a bias. And the user can say, this is how much I trust my opinion. I am 100% sure that what I'm saying is right, or maybe I think 25% I think I'm right, and that is used as a probabilistic prior to help provide confidence to the user input. And this also helps to build trust, because now the user has some level of control about what's going on. And so this is that paper on human in the loop. Right. So this is the work that Jay created and is continuing to be done by Howie and Brian, and it's doing autonomous depositing corrosion-resistant films and then testing the corrosion-resistant properties. This is another cool project. This is, the video works. In this case, we're controlling two assets. Is this a video? No, the video doesn't work. In this case, we have control over two things in a neutron scattering facility. We ran this at NIST and Oak Ridge National Lab, the two dominant, two main neutron scattering facilities. It can control both the angle of the detector and the temperature of the sample. And the goal here is to do the minimum number of experiments to figure out what the fundamental physics is of the magnetic sample. This is the Autonomous Formulations Lab that's being funded by NSoft, this consortium of many companies. Again, so this is like mixing liquids and then running the liquids through a tube that passes in front of an X-ray diffraction beam or neutron scattering beam, so that you can then characterize how the molecules are forming together, and then the properties. And so now you can relate the synthesis process structure property relationship of these materials, instead of just trying to go from how you made the material to the properties, which I hope I've made an argument that that's not the best way to go about doing things, but that's the dominant way of that most people in autonomous science do things. This is the new self-driving direct air capture synthesis lab run by Austin and Howie. So if you have interest in any of these, this is one of the cooler things. So in this case, this is I'll talk a little bit about this. So we have a pulse laser deposition system. You stick some target in the chamber. You have your wafer in there. A laser comes in, pulse of laser comes in, hits the target, hits the pure source. So let's say it's cobalt. That energy hits the cobalt. Cobalt atoms come down and deposit on the wafer. This can, you can have laser hitting a bunch of different materials, and the atoms fall down onto the wafer, and they start to the wafer is heated, and you start getting atomic layer by atomic layer growth of materials. And we have an electron beam bouncing off the surface, and from that electron beam, you can actually get measurements that tell you what's the surface roughness and what's the lattice structure of the materials present at the surface. And so then you can start optimizing synthesis and processing of the system to optimize materials. And that's exactly what we were able to do with 3 material systems so far. And now we actually have 3 of these chambers. We're working on having them work together. So the goal here was these materials that we're trying to make typically collapse into a more stable form, but we want that unstable form. So can we optimize the synthesis? The parameters like the laser power, the laser speed, the atmosphere in the chamber, right? The heat under the wafer, all these types of things to ensure that we get this specific non-stable material. And we were able to do that for 3 material systems. Um, and then we have another one, which is in this case, what we did was we have a 3D printer with an X-ray diffraction image, X-ray imager in the system, so we can see defects as they're forming, and then optimize the 3D printing. And the fun thing is, I don't know if I have the image here, is that the company didn't want us to do this. So what we had to do was one of the students, he put like they wanted us only to interact with the equipment through a physical interface by turning a knob and pushing buttons. But we wanted API control. They said no. So then we put a NEMA, or the student put a NEMA 17 to rotate the knob. So now we can control the knob through computer control. And we have motors that just push the buttons when we want to push the buttons. So now we have autonomous, right? We can build an autonomous system with this, right, this thing. Let's see, what else? So we can optimize materials to, okay. And the last things I want to mention. So the question about having these systems work together, this is one of the cooler things. So one of the things my favorite things that we've done recently, this is a tool called Multitask, which is named after a Marvel superhero. He's normally known as Multiple Man, but one of his previous names was Multitask. And his superhero power is he's a scientist. But what he does is he can duplicate himself. And each of those dupes, he calls them dupes, then becomes an expert in a specific field. So in this case, right, one scientist becomes the expert in, let's say, X-ray diffraction, another one becomes an expert in pulse laser deposition. And then all these duplicates work together in the lab. And so what I've shown is that each of these different systems, all these different systems, they're controlled by physics-informed AI, but different physics-informed AI. And those physics conflict, right? The same AI that runs a read and PLD system has different rules than the system that's doing phase mapping. So you can't have the same AI running all these different systems. It has to be different, bespoke physics-informed AI. To get that boost. So then the question is, can we get these AIs to work together and accelerate even more beyond the physics informed, right? So we get the boost of autonomous, we get the boost of physics informed. Can we get an additional boost of, and also human in the loop, can we get additional boost of having the AIs talk to each other and work together as independent agents that they can make decisions on their own? And in this case, you can form teams and have them work together. And what we found was that you can actually have that through going over this very quickly, by having the agents share data, you get a boost. By having the agents share data and work together on deciding which experiments to do next, you can then buy it. So like this agent can know which experiment to do best, experiment to do next would benefit them. This one knows which experiment would benefit them. But maybe you could bias those experiments a little bit more towards each other so that that you get some added knowledge that boosts the other people. And then we have this other algorithm called Sage, also named after a Marvel superhero. Her thing is that she can combine knowledge across different sources, so like Twitter and Facebook and CNN, whatever, right? Like collecting all this data and build one model of the universe or of the world. In our case, we have a materials lab that collects data, magnetics data, optics data, electronics data, structure data, X-ray, neutron scattering, all these different types of sources of data. They're very different. How can we combine all of this data to build one central model of the synthesis process structure property relationship? And that's what Sage does. So it basically wraps all of these data sources in a probabilistic framework. It basically asking what's the most likely probability of observing this data given us, in relationship with each other under assumptions, under the assumption that this is important, that the phase diagram is important, that the structure of the material impacts the properties. And so then what this tool allows you to do is combine a diverse, you could have 10 different data sources, all different, and you can allow them now in one model to combine all these different sources into one probabilistic model with uncertainty quantification propagation from beginning to end to tell you what, to give you one model over the entire lab. And then I guess the last thing, I want to say is that we also have this toy system, which we've been using in our class called Legolas. Originally, it was built out of Legos, and the kids use it for building, for building and running an autonomous system in the lab. Now it's mostly 3D printed. I can show you again the system behind me over here. And so it costs $300 in parts, and there's now an open source community built around it with universities, companies, and government labs around the world working together to boost this, and primarily with the goal of making a tool that's as cheap as possible that allows people to enter into the space of autonomous science, from their home, or if you're in if you're in a low income country, you can start getting into this space. Um, yeah, and right, and we showed this that you can even use this to discover mechanistic models using symbolic regression in collaboration with this, right? So the AI has control of symbolic regression. In this case, it was able to discover the Henderson-Hasselbalch equation with a few experiments, right? So it's optimizing each experiment to figure out what's the underlying physics. And all of our AI is being built into this one model, one library called Hermes. So if you're interested, that's on GitHub. Okay, I just rambled through a whole lot of stuff, but it was very high level. If you're interested in any of the guts of any of this stuff, please feel free to contact me.
All right. Yeah. Gilad, that was a really great talk. Thank you. There are a couple of questions. You did a good job of looking through the chat. There are a couple of questions that you didn't quite nail, and so we're going to start there. One of them from William Treherne, particularly, it was a little bit earlier on in your presentation. Do you do a throughput study for the experiments in the lab? I assume this is in with relation to, is autonomy worth it?
Right. Yeah. So, okay. Yeah. So I see all of these. Yeah. All these questions came in. So yeah, William, thank you for all of these. So do you do a throughput analysis of the machines? Yeah. So we compare. This is an excellent question. So what we do is uh, we compare the performance of our algorithms and our autonomous systems to a few different things. One is, if you did exhaustive experiments to map out the space, how do you perform? And in general, you get like an order of magnitude or two orders of magnitude boost. But then we also say, if you were an expert in these systems, how would you do it yourself? And so then we compare to that, right? How would an expert do this? And so then typically what we'll see is the boost uh, goes down to, instead of like two orders of magnitude, it's something like 5 to 10 time boost in a reduction of the number of experiments you're doing and the time that you're spending and the resources you're spending, right? So in this case, we see that, so throughput here is defined as knowledge out as a function of resources, time, and experiments done. And so what we see is that relative to a exhaustive exploration, you see a dramatic boost. Relative to a sort of a Edisonian approach where you have experts running the experiments, you see still an exponential boost. How do you manage very different throughput experiments? For example, CREEP is very low throughput experiment compared to something like density measurements. Okay, so yeah, we tend to focus on systems where measurements take from a lot of minutes to days. We haven't focused on problems where you might have something like creep that might last, weeks or months. So Uh, but multitask, when combining data across these different platforms, has a built-in scheduler. So and Sage. So right, so Sage, if you have one data stream that's bringing in more data more quickly than the other ones, that's going to have a bigger impact on the model. And then you have these other slower data sources that will be provided. Maybe you have data sources coming from TEM where you have to, do a lot of sample prep. So that data is going to come in much slower. So then that data will just have a slower input on the full model. Um, but yes, for selection of experiments, we have this scheduling aspect in multitask. For knowledge integration across slow versus fast systems, it doesn't really matter as long as you have the main thing there is uncertainty quantification in your measurements. You want to properly quantify the uncertainty. Um, if you don't, the Sage will quantify it for you. It will give you a rough approximation of your uncertainty, but it's good to have that uncertainty built in to your data. Um, okay, how do you get around hardware software limitations set by companies? Yeah, so you just hack the equipment. So, I mean, if you talk to most of the folks, I don't know if Helg is one of the speakers for the seminars.
Not this year, but now that I think
Okay.
about it, I should have invited him.
Yeah, so he can talk a bit about also hacking lots of pieces of equipment. So often that's the best thing to do is because most industry won't provide that ability for API control. So then you have to figure out how to hack the equipment. Once you can, yeah, and this is an effort that we're trying as a government, the U.S. government is trying to figure out ways um, to try to leverage purchase power to improve, to get better API control. Products producing significant amounts of data. Is there data management and governance practices in place? Given the modular lab approach, are you sharing through cloud-based storage? So currently, no. But this is something that we're teaming up with somebody specifically on this. We have an expert on this in the group, Zach Trout. He's an expert on data governance and sharing and all these things. And because of that, we are starting to employ that's starting to be built into these systems. So we have a plethora of systems and we're starting to build the data infrastructure to support them. Does the SAGE algorithm work with Bayesian neural networks, Gaussian processes? What kind of model do you use? Is this an active learning framework? So SAGE is a fully probabilistic framework. So the algorithm is up here. Um, uh, it uses, so it doesn't use neural networks. Um, my bias is more towards statistical learning, while other people in the group have a bias more towards deep learning. So Sage is very much in the sort of Gaussian process approach to things. So it actually does sampling of Gaussian process it has some probabilistic processes built in. So it is a fully probabilistic. It's a fully probabilistic process that is piecewise and uh, let's see. I don't know if I'm answering the question. Um, is this an active learning framework? So this model doesn't have active learning in it, but because it's a fully predictive algorithm. So this is used at the predictive layer, right? So most autonomous systems have three layers: analyze past data, make predictions based on past data, and then make decisions. So this fulfills that middle bar. And then the Cameo active learning scheme of exploiting knowledge of the phase diagram to optimize material properties can then be used on top of this, right? So I didn't show a slide on how that algorithm works, but right. So the intention is to combine those two. Um, uh,
Gilad,
yeah.
um,
Oh my God, so many questions. Okay.
okay.
Yeah,
So it is
we're
one
running out
o'clock.
of time.
Our students actually have to transition to the practical.
Okay.
I want to encourage Runza, if you could, to see if you can get down the questions from the conversation. And certainly encourage any and all folks to reach out to Gilad. He's awesome and he's good about responding. So let's take an opportunity to share our, joy. Let's thank Gilad for the presentation. And yeah, awesome. Thank you so much for your time, Gilad.
All right. Thank you. Thank you, everybody.
Okay.
Thanks
Have a great
everyone.
day.
Thanks for inviting us.